What is impedance in electrical engineering fundamentals? Imagine trying to push water through a pipe that has some bumps and narrow spots. That's kind of what impedance does in an electrical circuit. It measures how much a circuit resists the flow of alternating current. Now, this isn't just about resistance, which always opposes current, but also about reactance, which depends on the circuit's inductance and capacitance. Resistance stays the same no matter what, but reactance changes with the frequency of the signal. In simple terms, impedance combines resistance and reactance into one number, measured in ohms. It tells us how much a circuit opposes AC current overall. Resistance is the real part of impedance and causes energy to turn into heat. Reactance is the imaginary part and is caused by inductors and capacitors in the circuit. Inductors store energy in magnetic fields and create inductive reactance, which makes the current lag behind the voltage. Capacitors store energy in electric fields and produce capacitive reactance, which makes the current lead the voltage. Mathematically, impedance is written as Z equals resistance plus J times reactance. The letter Z stands for impedance, R for resistance, and X for reactance. The J is the imaginary unit, which helps us handle the phase difference between voltage and current. The size of impedance, called the magnitude, shows how much the circuit resists AC. The phase angle, which tells us if the current is leading or lagging, is calculated using the arctangent of reactance over resistance. From the perspective of electromagnetism and fields, inductance and capacitance are what create reactance. Inductance is how much a coil resists changes in current, and it increases with frequency. Capacitance is how much a capacitor resists changes in voltage, and it decreases with frequency. Because of this, impedance varies with the frequency of the AC signal. This frequency dependence is what makes impedance so useful in designing filters, tuning circuits, and transmitting signals. In real-world applications, engineers use impedance to design power systems, communication devices, and signal processing equipment. By measuring impedance, they can see how a circuit behaves and adjust components to get the desired performance. Understanding impedance helps in controlling voltage, current, and phase relationships, which are all vital for efficient and reliable electrical systems. So, in essence, impedance is a complete way to describe how a circuit opposes AC current, taking into account both resistance and reactance. It plays a key role in how electrical signals are managed and how circuits are built to work smoothly across different frequencies.